In the previous video, we have splitted the data into training and testing, and also splitted the testing data into data and output. So in this video, we are going to build a model using RPath library. So we are going to use ID3 algorithm for building that library. So when doing that, we are doing RPath of, we are writing class and this symbol and dot. So this indicate, so let me come back. So we are using data is equals to cancer train. So you are using the training data for building this model, and in that we'll write the target variable or the target column here, and this the delta symbol and dot indicate all columns. So if you are doing only with few columns, you need to write them, but in this case we are using all columns for training. And method equals to class, and parameters is equals to list of. So here we need to see here that we are giving it as split equals to information. So I told initially that this RPath model by default uses cart algorithm for building the decision trees, but in our case we are doing ID3 algorithm. So we need to indicate the RPath that we need to split based on information. So information here indicate information gain. So let me run this. So it will build the model for us, and we can also print it out. So you can see here star indicates terminal node, and there are 457 as we already saw, that are the number of entries in our training data. So you can go through this picture for more information. So after doing that, we need to analyze the tree or the decision tree that is built. So let me print it. So you can see the variables actually used in decision tree construction. So that is bare nuclei, BL chromatin, cell shape, cell thickness, mark adhesion, and normal nucleoli. So it has used 1, 2, 3, 4, 5, 6 columns for building the decision tree, and others are not used or not needed in building the decision tree. So they are redundant, or can actually remove them if needed. So these indicate the CP and error, so relative error. So you can see that as the CP is decreasing, so the relative error is also going down. As the CP is increasing, the relative error is also increasing. So here n split indicates the number of splits. So when the number of splits is 0, so the CP is also high and the relative error is also high. When the number of splits are increasing and the tree size is 6, so we'll get the relative error as 0.048485 and CP as 0.01 finally. So the algorithm will stop over there. So let me plot the tree. So we can also see whatever we have seen before. So the relative error versus CP and also size of tree. So here you can see 1, 2, 4 and 7. So there is a 6 in between. So after 6, even if you go further, the relative error is also not going down as the line has become parallel to the x-axis, and so we'll stop at 6. So size is finalized as 6 and you will stop over there. So we'll see the summary. So summary indicate node number, so what is the predicted class, so expected loss and probability of node, different things, and class count, so how many classes are there at that node, so ones are how many ones and how many zeros. So on the top will also show how many observations. So in total 23, and in 23 how many zeros and how many ones. and their probabilities are also included in the right below them. So let me go back to the next line. So you can see that we have used 6 columns, so they're actually built like this. So cell shape on the top, first divided based on that. So less than 4 this side, greater than 4 on the right, and bare nuclei, so less than 3 here and greater than 3 here, and cell thickness less than 7 this side and greater than 7 this side, and again normal nucleoli less than 2 this side, greater than 2 this side, mark adhesion less than 6 this side, right, greater than 6 this side, BL chromatin less than 6 this side and greater than less than 4 this side and greater than 4 this side. So these are the leaf nodes. There is no further splitting, so the decision is made based on what we get at the leaf nodes. So let me print. So this is nothing different than before. So you can see what is the P. So P is actually the predicted class of the tree model. So you can also view P. So you can see it is a P is a factor with 2 levels. So its value is either 0 or 1. So you can also see the structure of P. So there are 2 levels, 0 and 1. And finally we can see the first variable, that's nothing different, the same. So let me plot the confusion matrix. So this is the main part of our project. So we'll have so many things that we need to analyze in our project in the confusion matrix. So confusion matrix and statistics. So we'll see reference. So reference indicate the true output of the data. So 288 are actually 0 and predicted as 0 by the model, and 4 are wrongly predicted as 0 when they are 1, and 161 are correctly predicted when they are 1 and actual is also 1, and 4 are wrongly predicted as 1 when they are 0. So when we see the accuracy, we got 0.9825, and these are the different things you can look into, but they are not important as of now. So sensitivity is 0.9758, specificity is 0.9863, false predict value is 0.9758, 0.9863 is the neg pred value, and finally this is balanced accuracy important. So balanced accuracy indicate that when we do the same algorithm multiple times, so we'll get a accuracy which is actually true rather than random. So when we do one time, we may get one accuracy, but it may not be true finally. So in this case, the positive class is taken as 1. So then next one is to performance estimation. Let me do it in the next video.